I want to give an update on some things that Mike and I have been working on with respect to OSLF. One of the efforts that I've been pushing towards is to go ahead and look at it from a naive type theoretic perspective as well as the categorical perspective, because the naive type theoretic perspective gives an interesting angle on efficient implementation. So I'm going to try to go through, well, I will go through what one approach to an implementation that is purely syntactic. So that's what I want to talk about as soon as the water boils and I got my hot drink in my hand. But essentially, what I'll do is I'll sort of sketch out transformations that can be done to a type level specification. I will avoid, just for the purposes of this discussion, the operational semantics side. I've talked about that quite a bit, so we know how to do that. We know what we're doing when it comes to the introduction of the modal formulae, and we know what the desiderata are in the sense of that we have a notion of substitutability that works with bisimulation, right? So those are the goals when it comes to the behavioral side. So I'm just going to talk about the structural side and the container side so that people can get a sense of how this is fitting together, at least on those fronts. So let me just stop and check in and see if people understand what I'm mumbling on about here.
Yes, that's great.
Okay, cool. All right, looks like the water is just about boiled here, so I'm gonna take 10 seconds to grind some beans and pull my shots. So 1 second. Actually, I can't, while I'm doing this, I can say a couple of things. Intuitively, we sort of know what's going to happen, right? So there's going to be a data type specification for the syntactic entity that is the representation of the state of a computation. That's essentially what every rewrite system is providing, is a syntactic representation of the state of a computation, right? So you can think of a process expression as, for example, or a lambda expression as representing the state of a computation. And then the operational semantics tell you how to get from one state to the next. So a lambda term or a row calculus term or a Java program plus the state of the virtual machine. All of those things are descriptions of state. Does that make sense?
Yes. And when you say without operational semantics, it is mean without rewrite rules, or
yeah. I'm saying in this discussion, I'm not going to talk about the rewrite, how we get the formulae that are related to the rewrite rules. I've gone over that ad nauseum, and we kind of know how to do that. I'm just going, for the purposes of the discussion, I'm just going to talk about, like giving, we'll talk about the general strategy, like given a type level description of the structure of a state, how do we turn that, so that's going to be an individual state, right? How do we turn that into a logical formula that's going to give us a collection of states?
Mhm.
Right. And in fact, this has lots and lots of applications, right? I mean, even in quantum mechanics, people are often writing the Bra-Ket notation, indicating not just a single state, but they really would like a bunch of different states, right? So they'd like to write a formula that says, you know, these range of states and these range of co-states or dual operators. So just one second here, I'm going to mute while I grind the beans. Okay, so the shots are being pulled, and I don't know if you guys do this, but for my morning meal, often I like to have miso. A little bit of miso soup keeps me warm and full all day. It's very useful. That and a cup of coffee, and good to go for a long time.
I heard that a good miso is difficult to prepare.
It is difficult to prepare, but you know, well, first of all, we have access to a wide variety of really, really good misos, because Seattle is home to so many different Asian subcultures. So there's lots of in fact, this weekend I was at I went to Uwajimaya. A friend of mine and I went to Uwajimaya and got a bunch of vegetables that might traditionally go into a Sichuan hot pot. And we brought them back, and I learned how to make traditional Sichuan hot pot. So I'm extremely happy about that. But while I was there, and the reason I mentioned in the context of miso, while I was there, I was just counting the number of misos in the. There was so many misos in the. Yeah, it was. So the miso is a good misos are good, easy to come by, and then I do this thing where I just take a spoonful of the miso and I mix it with some sesame oil and secret aardvark sauce, which is one of the Pacific Northwest best kept secrets in terms of hot sauce. It's just a fantastic hot sauce. It's the best I've had in my travels. And so those two, and then just, you know, you mix the oil and the miso and the hot sauce together, then you add the hot water, and it is very warming and filling. It's really quite good.
Nice.
Yeah, I like. Okay. Yeah, I've been thinking about a segment on the climate and coordination call where we go through doing one small tiny thing in a way that you don't have to depend upon the supply chain. Like, you know, how do you actually make miso yourself, like from scratch, right? Or how do you extract honey from a beehive? Something I know a little bit about, because unfortunately, the dependencies on the supply chain are, we're not going to be able to rely on those in the same way in the next couple of decades. So,
Yeah.
so yeah. I mean, it's not like we can cover all things, but being able to cover a few things and get people in the spirit, you know, maybe we can get more people to do that sort of thing. I know there's lots of videos like that on YouTube. All right.
Mm-hmm.
Without being too prepper, not interested in conspiracy theories or too much apocalypse, but all right, let me switch devices and bring up some slides.
So I just want to remind people in the context of, so we'll carry this out in the context of an actual example. This is the type level description for the core row language, which is row calculus. So the row calculus states, which are row calculus process terms. And this is the core type level description. I've used a kind of bastardized notation where I'm using both BNF, but the BNF is parameterized. And I'm allowing myself to use products. But you could easily translate this into legal Scala syntax or legal Haskell syntax, I think, without too much trouble. Does that make sense? This is
Yes.
it's readable. Okay, and then so this is the one without the tying the recursive knot. All right, so we're saying that the notion of process depends upon a notion of name. And then you can either have the zero process, so that means the unit type, right? So there's a single constant element of the unit type, which would represent the zero process. Or, and here I've done syntactic for as opposed to semantic for comprehensions. So instead of having a function type here, I've done a product type. And the reason I've done that is because it's not all functions that we admit, right? The functions we admit are only substitutions. You could have all kinds of crazy functions which take a name and produce a process, but we're not interested in those. We're only interested in substitutions. So in some sense, it makes more sense to model the state in terms of a product, and then put the state transition, put the substitution and its specification into the state transition, as opposed to into the specification of the state. And then here, what we've got is the output, right? So you have a name and you've got a process term. This is the parallel composition, so it's two process terms. And this would then be a name. And again, names are a type parameter. Then tying the recursive knot would be, so we're really applying a higher order operator, R, reflection, to a type constructor, which is parametric, right, in some thing. And that's reminiscent of how monads work, right? The monad as a type operator needs to take a type which itself is parametric. So it's very similar, right? And what the reflective operator does is it removes one hole. And so, so you can think of reflection as kind of dual to differentiation, right? So reflection is very much like integration. So if differentiation adds a hole to a type, then reflection removes a hole, right? So we're going to get rid of this type parameter here. right? And the way we do that, of course, is to wherever we would put the X, we're going to replace it with a recursive reference to the thing on the left. So in the case here, where we have an X, we're going to put an RP, but we know that it's not really an RP, it's an N of RP, which means we're just tagging, right? So we want to make sure that it's not just a process, but it's a name. So we differentiate between names and processes essentially by a single tag. All right, so then this mimics exactly all the terms, right? Where we've replaced X with something that is fixed. There's no variables here. There's no X's in here, right? And this is not really an X because we're instantiating in at RP. So you can think of reflection as getting rid of type parameters. And so in this way, you can think of it as like the dual to integration. I'm sorry, to differentiation of types. And so it's in some sense behaves like integration. All right, and then just for fun, I have sort of sketched out how you compare this to Rolang proper. So one way to understand Rolang proper is to understand that we're going to expand this core type characterization in such a way that that we allow for the enrichment of row calculus with sort of built-in operations and a class of built-in names, right? So 2 years ago, I gave a talk on design level thinking for process calculi. And so this is just a syntactic version of those diagrams. So notice that with the built-ins, so like the numbers, strings, and a variety of other built-in types, we're going to add them in the same place where we added 0, right? 0 we pulled out of thin air, right? It wasn't a parameter here. But what we're going to do is we're going to instead put a parameter here, and that's going to represent all the built-in things. So that would be 0, strings, numbers, bit vectors, blah, blah, blah. That's all going to be packed into here. So you could think of this as a giant sum of all of the different built-ins. Right. And so then basically all we do here is to make sure that we carry along the Z when we make the recursive calls to the P type. And you can still do the same recursive closure, right? So notice that we're only getting rid of one hole, right? We get rid of the X. So Z is something that we don't get rid of. You'd have to reflect on the Z in order to get rid of the Z. So that's that. And then the other thing that we want to do is to expand the name type so that it's not just the recursive calls to the process, right? But it also has some underlying name types. So URIs or addresses, SHA addresses, or de Bruijn numbers or strings or what have you, right? So all of those are, this would be a big sum of all of those. And so either you have built-in names or you have the recursive process structure, process reference.
And can I ask you, in a Z, you say there is all ground processes, and can we? I mean, why? Can we do this in names and just say?
No, that turns out to not work.
Okay.
Yeah, what you really want is for values to be processes in the same way that values in Lambda are Lambda expressions.
I'm thinking because we have this recursive loop, we can always turn them to process, even if there's like stuck with names.
Yeah, exactly. But if you start them as names, then this is exactly why it doesn't work. If you start everything as a name, then what happens when you dereference them? Dereferences. Yeah.
I see. Okay. Got that.
Okay, so that gives you some kind of conceptual playground, right? So it's a fairly big playground. Without saying very much about what the type definition language is, or the data type definition. So anyway, so that but kind of by example, we've sort of said roughly what the space is, and now what we're going to do, in the same way that I kind of mentioned in the Casper stand-ups, where we talked about running OSLF on the data type for the trees. We're going to do the same kind of thing. So what we really want to do is we want to replace everywhere where we have a thing, we want to replace it with a collection of things. And we want someone to give us a specification of collections and how they work. Okay, so if I have some collection, say T, which is going to be a parameter to the system, then I want, instead of a single X, I want this to be a T of X and a T of X and a T of P. And so what we're really doing is in the same way that we're working with operators on type constructors, we have an operator on this type, let's say L of P, right, which takes it from states, from individual states to a logic of states, right? So L of P, so let me just sketch this out for you before we move on to the next slide. So I'll do this down here. Right, so I'm going to have L of P, but it's also going to take a collection parameter, right? And then this X, so the collection has to be parametric in X as well. We know that P has to be parametric in X. And then L is going to operate on these two. And so it's going to then do a T of X, right? Why is that? Well, we want the T of X because we're interested in collection of the T things of states, right? So it's going to be like that and like that. Right? Is that making sense? And then we'll put this all the way through.
I was thinking you'll write T.
This should be L.
Of
This should be this should be recursive, right? So it should be L. That was a typo.
Oh, I see.
We have an L of P of T. Oops. Of X, and then L P T X and this would be T of X. And I'm sort of glossing over the name stuff. And then, you know, but one of the things that this recursion is saying is that we get collections of states by looking at structured collections, right? So it's like we have a 4 comprehension skeleton, and we're going to put a spec for the kinds of names that we can synchronize at, and a spec for the kinds of variables that we're willing to bind, and a spec for the kinds of continuations. And similarly here, we put a spec for the kinds of names we're willing to synchronize at, and a spec for the kinds of processes we're willing to put out. Right, so you see, we've jumped up a level. This describes a single state, and this describes collections of states. And we're saying that collections of states decompose into structured, imposing a structure on collections of things, including collections of names and collections of states. Right, so that's, now you can see that this was a completely mindless syntactic operation. We went from here to here without thinking. Right, does that make sense? So that's completely algorithmic. There's nothing magical about it at all. And now we want to do the same thing. So I want to be a little bit careful when we and this has been in some sense so much of what has been the challenge for Mike and I. So I'll describe 2 of the challenges for us over the last several years, which is to teach, and it is astonishing that the community has no consensus on this. Right, we are like almost we're 90 years into computing. You know, like this 90 years since the lambda calculus, 90 years since the Turing machine, right? And and we don't have collections and types all sorted out, and to prove that that hasn't been sorted out. If it had been sorted out, then the Scala collections library would not have been rewritten 3.5 times, right? It would have gotten it right the first time. But the fact is, and that's just an example of one language and one, you know, investigation into the relationship between types and collections. There's been a similar upheaval in Haskell, and a similar upheaval in many languages. An example of a language where people have really suffered because there is no consensus within the computing community about how types and collections and instances all fit together, is the language R. And R, which is an open source version of the language S, which is a basically a, lambda wrapped around statistical operations. That sits at extremely high value libraries, such as the bioinformatics libraries that are used by, say, the Fred Hutch Cancer Research Institute, and the Institute for Systems Biology, and a wide range of other bioinformatics science centers. And also it is used extensively within the financial community. But ours, zoo of or maze of it's just a bag of a jumble of relationships between types and collections is horrific, so much so that it causes enormous pain in terms of R's performance as a language. And you can see it in the implementation because the implementation never really knows what type is of data it's dealing with. And so there's, in the implementation, there's a defend, which is divided in the same way that, we have our implementation of R chain in terms of both Scala and Rolang. So R's implementation is split across C and R. And you can see that there's all this, we don't know what type this really is, defensiveness at the R level. And then again, the same code is happening at the C level. We don't know what this type this is, so we have to defend and apply potentially reasonable conversions. And if we get past all of these defense mechanisms and we still don't know what type it is, then we actually throw an error. And this causes enormous performance degradation for the language. And then on top of that, there are copy on write semantics, which means that normal program transformations, which should leave the program unchanged, actually cause fantastically horrific complexity explosion in the language. And this has impact on the financial industry and the bioinformatics industry to the tune of hundreds of millions, if not billions of dollars. So if you add up all of the money spent on the errors because there is no consensus about how types and collections work, it's in the tens of billions of dollars, if not the hundreds of billions of dollars. And so to me, it's so that's good, solid, objective data that you can collect, that there is no consensus in the community about how all these things fit together. Right. So I'm not some crazy person saying, oh, the types and the collections, they don't fit together well. We don't understand how this actually works. In point of fact, the community really doesn't understand, and you can measure it in terms of the impact in creating production level tools. And so, it's not, that's in part, it's not an excuse, but this is in part why Mike and I have spent so long. I mean, we spent, the better part of 10 years trying to make sure that we have a convincing story about how the collection part and the predicate part and the type part all fit together. So that's a digression for me to explain, where this T comes from and what we might expect. So let's give a simple example, right? Most of the time, when we're talking about predicates, when we move from a individual state to predicates on states, people think of that as a shift from individual states to sets of states. But we know that there are many different kinds of logics, and not all logics have natural set-based interpretations. A powerful example that has strong consensus within the community is linear logic. Linear logic, one should not think of the semantics of linear logic a priori as grounded in sets. You can give set-based interpretations, but it's probably better, and Girard himself, the inventor of linear logic, has proposed that it goes the other way around, that linear is more fundamental than sets, and then sets are built on top. And there's good evidence mathematically for that position. So the question is, if we are going to treat arbitrary collections, when can we think of collections as predicate-like, and what can we hope to gain? So I'll give you a hint that when we if we think of these specs as being recognizers of state, right? So in the same way that you have recognizers for a language, right? So automata that recognize languages, which is dual to generating languages. So if we think of them as recognizers for states, that will provide a reasonable semantics. So that's the key insight. So suppose that we didn't want to use sets for the collection type T here, but instead we wanted to use lists. Well, let's just give a type level specification of lists. So that we can have sorry, I'm actually doing trees here rather than just lists, because I can do lists of lists. So here I'm specking out a notion of a tree with ordered children coming out of a node in the tree. And if I want to have, so notice that I could have a guarded recursion here if I didn't have the empty tree branch, but that would force me to always have a node labeled with an X. So I add an empty tree, or I've got a node in the tree and its children. Is that clear?
Yes.
Okay, good. Now the thing is, this just describes an instance of a collection, right? But when we think about predicates, they're actually on the power set, not on the set, right? So so we need to go one level up from instances of collections when we're thinking about turning this part into a logical part, right? So we want to go from a T to a phi, and then this phi is what we are going to supply for this T here. That's a little bit of a mind twist, but this is one level up when we go to the logic. Does that make sense? So in the same way that predicates are on the power set of whatever your universe of states is, this is not going to be on a single collection of states, but on a collection of states. So it's the same idea. And now what we're saying is that that this is really I want a spec on the values that guard the node, and I want a list of specs of lists of trees, not a single tree, not a list of trees, but a list of specs of trees. So this is the right shape for the type level constructor that's going to be bound to a T here. So just to make it super clear, I'll rewrite this using phis so that you can line them up visually. Oops. Come on. There we go. So that gives you me running the algorithm step by step so that we get from the core type to a a type which gives us the logical formulae or the type of types that pick out fees or sorry, T's of states, right? So I did that completely algorithmically. There were no design decisions here. There was no thinking. Does this make sense?
Yes, yes.
Yes.
Okay. All right. So this is why OSLF, I mean, there's a lot more to it, but this is what's going on. Like when I run the monoid example where I start with monoids and I generate a logic for monoids, and then I write down an interesting predicate, like the predicate that picks out all the primes for the monoids, right? This is the algorithm that is making that example work, right? And you can see how if you have reflective representation of types in a language, then the implementation of that algorithm is straightforward, right? So this is why, back a couple of years ago, I was threatening to do an implementation in Agda, but I did an investigation of Agda, and it's like, well, Agda doesn't have the reflective capabilities that I need. So currently Scala is still the best choice for implementing OSLF because it has the ability to reflect and find the types, right? So types are first level entities in Scala. So if you give me a type like this, I can produce algorithmically a type like this, right? That's something I can do easily in Scala, right? That's like whatever, less than 1,000 lines of code. So that's the trick. But there are a few things that we have left unsaid. So let me. So one of the things that we've left unsaid is what does it mean to take a sub list? Or in general, if you give me a collection, so here I was using C on this page rather than T or phi. But if you give me a collection C, which is some type, then what does it mean to give a sub thing? And this is kind of important if we want to be able to interpret logical formulae like negation. So negation isn't defined for sets, but it is defined with respect to an overarching universe or set, right? If you pick some set, this is the whole world of all possible things that you could draw sets from, then you have a notion of complement with respect to that thing, right? So that really says you need a notion of a sub-gadget. So if you have a sub-gadget and you have an overarching gadget, then you could remove that sub-gadget from the overarching gadget and get what remains. But it turns out we have a very crisp notion of sub-gadget that works for a wide variety of types. So if the type is differentiable, so for example, suppose that I did my notion of list like this, right? So it's either the empty list or it's a list containing exactly one element, or it's a list containing two elements, or blah 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 blah, which is basically the sum as n goes from 0 to infinity of all the different in length products. Does that make sense?
Mm-hmm. Yes.
Okay, cool. So I can define a wide range of notions of sub things. So here's an example. Here's the whole list, say 4, 3, 4, 5, 7. And I could think of this as sub with respect to the whole thing, right? By taking a collection of positions, right? And in general, you can relate those collections of positions to the H derivative, right? Which allows you to give offsets with respect to where you poke your holes, right? So then there's a nice generalization of the usual notion of zipper. So I have an H derivative of the collection type, which is going to be allow me to poke holes in a wide range of places, not just in one place. And this has to do with the fact that there are iterated positions here, right? They're iterated uses of X, right? So I get an H derivative, which gives me this delta star, which I apply to this thing. So that gives me this gives me a notion of a mini hold context, and then I can plug the holes in the context with the sub gadget. These are the things that go into the holes here, right? And then I can either reproduce the whole list by plugging this stuff into that, or I can take this away from the whole list, producing the complement. So this gives me a notion of negation that fits with this type level description. So these are this is the type theoretic way of looking at what we're doing with the category theory. And sort of as I mentioned before, the advantage of looking at this from a type theoretic perspective is that we can see how the implementation goes in a language that's equipped with certain features relatively quickly. Does that make sense?
Yes, yes.
And we can see that just one last point, and then I'll take your question. So notice that the complexity of this thing relative to the complexity of this thing is not orders of magnitude, right? It's like, right? It's like 4 times the complexity, which means that running this algorithm on the realistic thing is not going to be that hard. I mean, we could easily do it by hand. It would be tedious, but it's not overwhelming. And so if we have computational support, then running this algorithm, with a Scala program on realistic languages is not hard. It's not going to take forever, right? It's quite feasible to do this on a language as complicated as C++. So that's why I've been pushing so hard to make this thing as mathematically precise and to make the scope as wide as possible, because you can just see for yourself that it just works. And then if you have a description like this, then type checking, like checking to see if a state, like one of these states, matches the type, is exactly the same as query, right? So I have a bunch of states, i.e. code in GitHub. I pull the code out. I check to see if it lives inside a given instance of these state specs. And if it does, then it satisfies the query, right? All right, now your question.
Now I'm thinking from some like very naive perspective. For example, when we define, when we have type of maybe a SQL table.
Okay.
And we can say that each column has some specific type, or text, or number, or
Sure.
And one level up is, I'm thinking that one level up can be that we are describing for each type how it behaves. For example, a number must be only positive or in some range. For text must be some specific length. And can I see that this L is basically we are somehow we are adding more information, but we are not doing this in a like arbitrary way. We are doing this as like algorithmically. We know how to do that.
So it's a good question, and in the remaining 6 minutes of the hour, I will attempt to answer it and widen the scope of the discussion. So one thing you'll notice that is missing here, that makes this distinct from predicates, is this is insensitive as to how you produce these trees, right? I have a tree of X's, but how did I get this, right? And as we've talked about many times in the Casper Stand-Up, there are essentially two flavors of methods of providing a collection like this. One would be to explicitly write out all of the elements of the collection, right? So if I'm told that I have to provide a tree of X's, then I could just write out that tree. And that could be quite tedious and even impossible potentially if I want an infinite sized tree. And so the other flavor is, instead of writing it all out, I give a rule for how to decide whether or not a given tree or a given element, a given X, is in the tree. And here we have no rule language for that. Does that make sense?
Mm-hmm. Yes.
You just simply said that there's a T of them, but we didn't say what the rule language is for recognizing when I have a valid instance. But, and this is where all the operational stuff that we forgot about at the beginning comes back into play. Okay, so what we're committing to is that collections come without an operational semantics, right? What we're saying is that the difference between program and data is program is where the SOS stuff lives. And this is only temporary. Eventually we'll be able to relax that. But for the time being, we say the difference between program and data is that rewrites are on programs, not on data. Data doesn't wiggle. Okay, so then we can go and steal the programmatic manipulation of data to provide a comprehension language for these collections. So we can build a notion of comprehension from the program syntax, right? So we extend this with an explicit thing which says how we say this is extensional, and then we build an intentional thing which is a comprehension syntax, so like a for syntax or a do syntax, or set-based comprehensions that on the inside of the comprehension can write down programs which will generate elements or recognize elements of the comprehension. Does that make sense?
Yes, yes. And what kind of expressivity we are introducing?
It's the expressivity of the programming language. So if you make your comprehensions, you know, Turing complete, you know, if you don't restrict your comprehensions in some way, then type checking may not terminate. Right? So you get more expressive power, and for the expressive power, you lose potentially the termination of the type checking.
I see.
Right. So that's the trade-off. And once you put those comprehensions in, then that answers your question about adding information like checking ranges of numbers and things like that.
And in the sub gadget, how this reflects? So I was thinking that maybe if we don't have this kind of computation way, we can only have a finite sub gadget.
No, you can have infinite ones. It's just you can't write them down.
Oh, I see. Because I was thinking like even numbers, and so we can have like even we can select even numbers, and then from this collection we can also say now we are taking all the even positions and even positions from that, and we can
Yeah. So the other thing that you could do is, instead of writing comprehensions, you could provide you can provide a set of built-in infinite gadgets.
I see.
Right. So if you had certain specific built-in infinite trees, then you could use tree operations such as product and intersection and blah, 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 to build new trees, new infinite trees from those built-in ones. So that would also get you beyond. So you know, it's essentially you could, in the same way that I've done. Well, we're out of time, but we can talk about this more next time. But thank you very much for your time and attention, and I'll see many of you on Dev Stand Up. Ciao, ciao.
Thanks. Bye-bye.